Homes Fit for Zero is the title, the strapline that I gave this talk, and that's it. Yeah, it pays homage to we're commemorating the start of the First World War next year, after the end of the First World War, Lloyd George came up with this Homes Fit for Heroes strapline, so that's the theme I've taken here. But the other parts of the context relate to zero carbon. We have a collection of logos on the screen here, which reflect the drive towards low and zero carbon economy, built environment, and also the climate change of the future. So we've got these twin stimuli, these twin drivers that are going to get in the way of our homes fit for zero. The third thing that's going to get in the way is that, as Lloyd George would have said, it's a free country, and we are free to festoon our houses with all this kind of stuff. I don't know how many megawatts are installed incandescent illumination there is on the front of that pub in Surrey, but because it's a free country, people do what they like, and we have to recognise that people are going to use energy. It's not just the buildings that use energy, it's what people do in those buildings that uses energy. In the now 2 minutes that I have left, I was going to tell you something about the work of our research group. I formed the Urban Energy Research Group a few years ago. It's got a number of multidisciplinary members of staff, 7 staff, about 15 students, a large number of publications, and plenty of research funding, and we do research on a number of core research themes, but we try very much to tie our research to the focus on the building user. Over that period of time, we've done a number of research projects, and it was my plan to tell you just a little bit about just a few of these. I was going to tell you something about Tarbase, something about low carbon futures, something about the Ares project, and something about our energy monitoring work. There's, as I say, there's not an awful lot of time. Focusing on 3 questions. So, structuring the talk around 3 questions. How can we refurbish existing homes? Tarbase was a project to look at how can we refurbish existing homes to reduce CO2 emissions from existing dwellings. And we developed a number of models for the performance of various technologies, focusing on variants precisely described buildings. So we set up a 2005 variant of a real building that really exists, and we fed into it our various input parameters of economics, user behaviour, social trends, future climate, CO2 intensity of the grid, Uncle Tom Cobley and all the rest, into a number of demand-side interventions. How do you reduce energy consumption? Followed by a number of supply-side interventions. How do you provide alternative low-carbon sources of energy to perform in a 2030 setting? I have this rather scary man down here with a camera. Hello! So Tarbase came up with a number of solutions, and we were able to look at ways, quantify ways in which we could reduce CO2 consumption, CO2 emissions by the energy-consuming operations, activities within our buildings, how we could reduce them by renewables, technologies, and the like. But skipping over the technologies, skipping over the technologies, people say, how much is it going to cost? And Sue's just mentioned costs just there a minute ago. So we came up with some costed intervention sets, and I quite liked these at the time because I was just organising the wedding for my daughter, and I was able to sort of say, well, this is the equivalent of 2 weddings, or this is the equivalent of 3 weddings, or 4 weddings, to tie it back. You could save 25% of CO2 for £3,500, you could save 40% of your CO2 for £26,000, or you could spend £32,000 and you could get a 50% CO2 reduction. Perfectly feasible to get these CO2 reductions, but it does cost your money, cost money. What are the occupants going to think about this? We did a little survey as part of this project. Don't get hung up on the detail of this, but there's a broad trend from the left to the right on that screen. You could buy a set of measures that will save you 60% of your fuel bills at a capital cost of 10 grand on the left, or you could save 20% at a cost of 1 grand. And you can see the shift from people who are not at all interested in the expensive one through to, yes, I would seriously consider that for the cheap one. So the users don't have that disposable money at their disposal to be able to make these deep cuts in CO2 emissions. And some headline conclusions: you can save significant quantities of CO2 emissions, but it's going to cost a hell of a lot of money for the entire stock. We estimated 340 billion, which, when you scale up what the figures that Sue just mentioned, that's not inconsistent. Where's that money going to come from? Is the Green Deal going to provide it? Well, don't think so. But if you're interested, we run the tar-based domestic model as a consultancy service. You could feed in your building or your stock of buildings, and we could give you some answers for that. Another specific project that we've been involved in, specifically looking at solid wall dwellings, is the Calibre project. There is an acronym lurking in there, but our part of the work was looking at one particular measure: mechanical ventilation with heat recovery. Great idea. Houses are leaky. You extract the heat from the outgoing air and you reuse it in some way. What are the challenges in doing that? Well, one particular challenge is making sure that you've installed the blooming kit well enough. There's some IR thermography photographs at the top corresponding to those actual images on the left. There's the MVHR unit, and when it's in operation you can see the heat losses coming out of the poorly installed ductwork. The uninsulated parts of the component and whatnot. And on the right, there's ductwork, and look at the heat leaking out of those. This is installed professionally by professionals who are doing this not every day of the week, but they're doing it for a living. Don't get me going. There's another problem, which is how leaky can your building afford to be before the MVHR has any effect? And these are some of the leakage sealing challenges. You've got to seal the envelope of your building because you want all of the heat leakage to go through your MVHR unit so that you can extract the heat from it. You don't want it disappearing out of the gaps around the pipes, through the leaky windows, behind the kitchen units and all the rest of it. And the nice snowy picture at the top there, that's the MVHR unit underneath that part of the roof, and you can see it's melting the snow. So clearly the heat is leaking somewhere. Some technical graphs here. Again, don't get hung up on the detail. They had to work so hard to leak tight this model building that we were using in Nottingham. But you can see from these bar charts that you've got to reduce the permeability of your house down to a figure of 5. The house started off with a figure of 15. It was a hell of a lot of work to get it down to 5, and only then are you beginning to save any energy. And it's even worse if you look at the CO2 emissions in the next picture, because you're saving heat, but you're expending electricity to drive the MVHR unit, and electricity has 3 times the CO2 intensity of the gas that was running the boiler. So you have to go further if you're looking at CO2 emissions. It's barely worth it. I certainly wouldn't put my Green Deal money into an MVHR unit when it's going to cost me £6,000 to have this level of effect. Yeah. My next research question, how can we design for the future? We have a climate change future. The climate is getting warmer. Other people have said the same thing. The present generation of climate predictions, UKCP09, are cast in a probabilistic turn of approach. And what that means, looking at the sketch on the far right there, is that they are predicting lots and lots of climates, each of which are equally probable. And we have a distribution within that range from the top to the bottom, and the whole output is coming in a probability density prediction. Much more difficult for building designers to cope with. You know, how do you handle the situation that there's a 90% chance of it being this temperature, but there's a 10% chance that it could be a much higher temperature. So we wanted to come up with a tool which would enable us to capture this range of performance. There's just three fairly well-known images looking at the rise in future mean summer temperature in the UK. 90 percentile on the right, highly unlikely to be greater than 7 degrees temperature rise in the central south of the UK. 10%, highly unlikely to be less than 2-3 degree temperature rise. So we've got potentially quite high temperature rises. So what we came up with was a tool which applies rigorous statistical analysis to the thousands of climates that would be predicted by these climate projections, and simplify that so that it could be used by the building designer with his or her dynamic thermal simulation for their home. And the results, a flavour of the results that we come up with. We've got a house that we've modelled this system on, and the graphic on the right there shows a sort of traffic light image of probabilities of overheating, applying a proportion of the occupied hours exceeding 28 degrees centigrade. You could put in any criterion. That happened to be the criterion that we used. So we've got a design tool which we'll be launching later this year, which enables designers to plug this into their dynamic thermal simulation software and come up with an estimation of this design before it gets built. How likely is it to overheat? So that's designing for the future. I think I'll cut out the other project that I was going to tell you something about, which is adaptation and resilience in energy systems, which is again looking at energy systems for the future. And this control doesn't allow me to skip over the other slides directly, but I will go. No, it's not even going to allow me to do it quickly. There we go. Ignore those. And let's go on to the third of my research questions. How can we make better use of what we've got? Well, that requires us to know what we're using. And here monitoring and fingerprinting, if you like, diagnostics is important. These are energy profiles from, in this case, offices. And you can see there's a sort of a base load in there which happens overnight. What's going on overnight that is consuming 0.01 kilowatt hours per square metre? Clearly, there's something going on there. If we could do something about that, we could identify what's going on there, then we can reduce it. The shapes of the peaks enable us, so we have a vision for a diagnostic tool that will enable us to go into these fingerprints and identify what's going on, target the user, back to the user again, target the user and say, here, did you know that your kitchens are using so much power, your offices are using so much power, you could take this down quite considerably. We've done it at the domestic level. We've got a technique for sieving out, filtering out the peaks to identify where the energy consumption is going on. And we're iterating, we're thinking, we're making progress on schools. We did a project on 80 schools across Scotland. and gave us a number of diagnostic fingerprints. So we'd be interested in getting more data, if anybody's got it, that we could apply this technique to. So I started with a political slogan. I'll end with a political slogan which Barack Obama copied from Bob the Builder. Yes, we can fix it. We do know, in principle, how to make homes for zero, fit for zero, but it's going to need a heroic investment to do it, and a bit of a change in people's lifestyle and energy-consuming habits and their attitudes. That was 10 minutes rather than 20 minutes, and I hope we've now got enough time for some question and answers next. So thank you for listening.